Question 10. Disprove the following statement. N squared minus n minus 1 is a prime number for any integer greater than n greater than 2. Prime factor, a prime number is a number with only two factors. Itself and 1. So in this case, the only way to prove this is to try some values. If we try n equals to 3, that should imply that n squared minus n minus 1 will be equal to 3 squared minus 3 minus 1. And that gives us 5. And that's prime number. Then we try n equals 4. That implies that n squared minus n minus 1 will be equal to 4 squared minus 4 minus 1, and that will give us 11. Again, that's prime. What about n equals 5? We're using n squared minus n minus 1 equals 5 squared minus 5 minus 1, so that's 25 minus 6, and that would be 19. 19 is a prime number. And n equals 6. Again, n squared minus n minus 1. We're replacing n with 6. So it's 6 squared minus 6 minus 1. That will be 36 minus 7, which should be 29. Now let's try n equals 7. Again, we have n squared minus n minus 1 equals 7 squared minus 7 minus 1, which gives us 49 minus 8, which is 41. Again, that's a prime number. N equals 8 will give us n squared minus n minus 1 is 8 squared 64 minus 8 minus 1, and that will give us 55, and that's not prime number. So we have basically disproved by counterexample. So we've used an example using counterexample to prove that that number is not true. Not all the numbers greater than 2 will be a prime number for n squared minus n minus 1. So therefore, n squared minus n minus 1 is not a prime number when n equals 8. So statement is not true. So I'll say statement is false. Question 11. We need to disprove the following. The root of x squared plus y squared must be less than x plus y. Well, in this case, it is best to find a counter example for which the statement is false. So in order to do that, we could say let x equals -1 and y equals 2. So what we now need to do is substitute those values into these equations, well, statements, expression by the way, to confirm if the left hand side is less than the right hand side. So I would say -1 squared plus 2 squared should be less than -1 plus 2. Well, -1 plus 2 is 1. Now let's see if we square root, well, the square root of -1 squared is 1 plus 4, so that will give us root of 5 less than 1. Now that's not true. In fact, root of 5 is greater than 1. Therefore, statement is false. Right, question 12. We need to prove by exhaustion that the product of any 3 consecutive integer is even. Right, few things we need to remind ourselves. This is called recall. So whenever we have odd number and we times it by another odd number, we always get odd number. Whenever we have a odd number and we add to odd number, we also get even number. Whenever we have an odd number and we take away from odd number, we get even number. Whenever we have even number and we times it by even number, we get even number. Whenever we add even to even, we get even number. And whenever we take away even from even, we get even number. So those are the nice recall. One more to recall is even times odd is always even number. Now, most of these recall we're going to use in this situation. But so we're going to let n be an integer. So we got n as an integer. So n is an integer. N is an integer. And then we have, if n is the first integer, the next integer will be, well, the integer before n will be n minus 1. And then we have n, and then we get n plus 1. And in this case, we are multiplying. So I put dots in there as times. Actually, let me put times in there. So we're multiplying these ones together. That's what it says. The product means times. So product is times. So to do that, we would have n into bracket n minus 1 times n plus 1. In maths, we have a situation here where we called, whenever we have a squared, you take away b squared, and the answer always is a plus b factor times a minus b factor. So this is called dots, which stands for difference of two squares. Difference of two squares is a squared minus b squared equals a plus b, closing bracket, open close bracket, times a minus b, brackets, close. And we've got that situation here. So we have n minus 1 and n plus 1 and n minus 1, which means we're going to have n squared minus 1 squared. And 1 squared is 1. So I would have n into bracket n squared minus 1. And if I multiply that out again, I will get n cubed minus n. So that's the formula for multiplying three consecutive integer together. But how do we prove this is going to be even number? Well, what we have here is n times n times n minus n. So this is the situation we have. Now, if we have, because n is an integer here, so we have to do 3 tests for this now. So 2 cases we can get, because we said integer. We can have even integer and an odd integer. So the 2 cases I'm going to do here will be even and odd. So in these 2 cases, I'm going to apply, so where n is even and n is odd. So n times n minus n, what would that be? So these n times n, well, odd, even times even. So where is that? So if I look on my list, even times even is even. So that times that is even. And even times even again. So that times that, so that's times n. But n is even. Or n squared is even, if you like. Or n is even. So let's say n squared. N squared is even and n is even. Even times even is going to give us even again. So that'll be n cubed. So n cubed is even. So that's even. N cubed is even. Because even times even is even. And then we take away even minus n. So even take away even shall be even. So in that case, with an n being an integer as even, the product will be the 3 consecutive integer of even integer will be even. Now let's try that with odd. N times n minus n. So n times n, odd times odd, n squared. This n squared is odd. Odd times odd is odd. And then we times that by n. So again, odd times odd will be odd again. So that will be n cubed, which is odd. And then we then take away odd from odd. odd minus odd is even. So that's even. So that's how you prove that, and hence the statement is true. So we can say statement is true.